Welcome to this Python project where we're going to build a crowd loading simulation that relies on the Duhamel integral. So we're going to start off basically understanding the Duhamel integral right from the very basics. So I'll explain it and we'll derive it essentially. But we're going to quickly move from that into building a simulation. And this is the simulation we're going to build. So this is a relatively straightforward simulation to build, but it models a relatively complex behavior. So what we've got is a crowd of pedestrians moving from one side of a bridge to the other, and we're simulating the dynamic response of the bridge in response to those pedestrians. So as I say, this is going to require us to get a good firm grasp of the Duhamel integral, and then we're going to sort of layer on different levels of complexity on top of that to ultimately arrive at this. So this is the final notebook that we'll end up with. It's going to have, obviously what you saw was just a simulation, but it's also going to have, naturally enough, what that simulation is built on, which is the crowd loading, which we're going to generate, which is this top graph here, and then the displacement of the bridge. So this is you can see the static displacement and then the dynamic component of that displacement layered on top. If we were to zoom in anywhere along here, we'd see that what you've actually got here is a static displacement with an oscillation layered on top of that. So we'll see all that. We'll get into the detail of what all that looks like shortly. So there's going to be a multi-part project. So it's going to start off, as I said, very simply. We're going to talk about at a concept level, what is the Duhamel integral? Then we're going to think about how we solve that integral to calculate the response of a structure analytically. Then we're going to move on and look at a numerical solution technique, which is far more versatile. And we'll talk a little bit more about that as we go on. And once we've done that, we're going to write some code that's going to implement a numerical solution, and then we are going to validate that code against a closed form or an analytical solution, so we make sure our code's running correctly. And then we're going to get into some simulation. So we'll talk a little bit about crowd loading. Well, first of all, pedestrian loading, the loads that are imposed by a pedestrian as they walk across a structure. Could be any kind of structure. We're focusing on a footbridge here. We'll then expand that into looking at a pedestrian crowd. So pretty much everything that we're going to be doing in terms of dynamic modeling here, we're focusing on a bridge because it's a relatively simple structure. But everything that we talk about is going to be easily generalizable to any structure that you want to simulate the response of. Now, the most obvious extension of what we do in this project is going to be the dynamic response, or simulating the dynamic response of a floor plate, a two-dimensional floor plate. So it's going to be quite a useful set of tools that you build during the course of this project. Now, if you're new to Python, that's not a problem. You can take this project without having done any Python coding before. Now, if you need some help getting your programming environment, your development environment up and running, I'll direct you to a set of videos on my website, a couple of videos that will walk you through getting your coding environment set up. So if you go to the Degree Tutors website, degreetutors.com, and you navigate to courses. Now the website might look a little bit different depending on when you go there, when you're watching this. But if you navigate down to this course here, the direct stiffness method for truss analysis with Python. So we'll just go to take this course and scroll all the way down to where you've got the videos. So you'll see the first three videos are basically setup videos. Now the one you want, if you're taking this project and you haven't programmed in Python before, is this guy, Getting Started with Jupyter Notebooks. If you click that, watch that video, it's only 12 minutes. That'll walk you through getting a Jupyter Notebook development environment set up on your computer. Now, obviously, if you've coded in Python before and you have your own development setup, that's fine. Use whatever you're comfortable with. But in this project, we're going to be using Jupyter Notebooks. Okay, so that's the plan. Let's just get stuck into it now and start talking about what is the Duhamel integral, just at a high level, concept level, before we dig a bit deeper and start, pulling it apart and deriving the equations. So the Duhamel integral method is basically just a simple method for calculating the response of a single degree of freedom system. Now, we can solve this thing numerically or analytically, right? So I'll just say here, we can solve analytically or numerically. And we'll say a little bit more about these two different methods now as we progress, right? In order to sort of pick apart how this Duhamel integral works, we have to first of all start off with the idea of an impulse, right? What is an impulse? So I've said here it's based on, the Duhamel integral is based on the impulse response. Okay, so what do we mean by that, right? Well, first of all, let's define an impulse. An impulse is just a large magnitude load that's applied for a short period of time. That's all it is, right? So we can kind of sketch that out next. So if I was to just set up an XY axis system here, where the x-axis is going to be time, and the y-axis is force, right? So force. So if I was to sketch an impulse onto this, what I might do is I'd have something like this. I'd say there's a force magnitude here, okay, and it's applied over a short duration of time. Okay, so I could say that force was applied at, let's just say, time t. It was applied for a duration of dt, very short duration dt, and it had a magnitude, let's just call it p here, right? So what we would say is the impulse is the shaded area. So the impulse associated with the force p applied for a duration dt is equal to the shaded area. All right, so I might say that the impulse I is the integration between t and t plus dt of the load p of t times dt. Now, another thing that you're going to probably come across is this idea of a unit impulse. A unit impulse is simply an impulse where that integral there, that area, is equal to 1. Okay, so we'll just say that for completeness because you're likely to come across that. How does that help us? Well, we get a little step closer to the end goal here by thinking about what would that impulse do to a single degree of freedom system, right? So what does it do? Well, it's going to generate a response, and we call this the impulse response. So let's just sketch that out. I mean, ultimately, we're going to derive an equation for this, but we'll just sketch it out for now. So this is just going to be some displacement time history. And we'll imagine we're dealing with a damped system here, so we're going to have a decaying sinusoidal oscillation. So some impulse is applied. Let's imagine it's applied at t equal to 0, and we get something like this, right? So we get a decaying oscillation. So we'll just say that this was the damped response of a single degree of freedom system to the impulse p of t dt. Right, now here comes the trick, right? The trick to this whole Duhamel integral thing. The trick is you consider the applied loading, whatever your applied dynamic loading is to your structure, you consider it as a sequence of impulses, right? So we'll break this down bit by bit. Right, now if I have a sequence of impulses and I know that each one of these impulses generates me something like this, some impulse response, a decaying oscillation, sinusoidal oscillation, well then to get the total response of the overall dynamic loading, which remember is just divided up into a series of these impulses, all I would need to do is get the response from each individual impulse and add them all together. And that's basically all we're doing with the Duhamel integral. So we'll say the total response is the summation of impulse responses. And so we're going to be using essentially the principle of superposition here. So let's visualize this then, right? So let's imagine we have some arbitrary dynamic loading. Well, what we're going to do is we're going to say, well, let's imagine, we go with different colors here, right? So we'll say, let's imagine we're going to break this up. I'm just picking some point in time along this loading history, right? And I'm saying, right, well, that there is going to represent one impulse. And I can calculate the response of my single degree of freedom system to that impulse. And then I'm going to come along and say, well, this here is going to be another adjacent impulse, and I'm going to simulate a response due to that guy. And this here is another impulse, and there's going to be a response due to that guy. And you basically continue all the way along your loading history, considering it as the sum of a series of impulses. Now, we can get the response due to each impulse and plot that individually, right? So let's imagine that impulse, the red impulse, was applied, and that was going to generate the same type of response that we saw here, right? The same type of response as this, right? A decaying sinusoidal oscillation. So that would be something like this, just a rough sketch. Good enough. Then we're going to come along and we've got this green impulse, and that's going to generate something like this. Again, same thing. And of course it continues. So you get the idea, right? So what we're basically saying here is that we're going to say that n impulses yields n free vibration responses. Right, so we go from the impulses down to the responses. And then all we have to do is superimpose, add up each of these individual responses to come up with the overall response that this original loading would produce, right? So that's that in a nutshell. That's the idea. There's nothing more to it than that. So we'll just say here we superimpose n responses to get the complete response to the original loading. Okay, and that's it, right? So our task now basically is to work out, well, what's the equation for one of these responses? Like, let's say take that blue one. What's the equation that gives you that blue oscillation? That's what we're going to try and do next, right? So what we're doing is we're working out the damped impulse response. Okay, so we're going to start off here with Newton's second law, right? So force is equal to mass times acceleration. So if we were to write that out, we're going to say f of tau, where we're just using tau here as an alternative for time t. So f of tau, it'll become clearer a little bit later why we're introducing tau in addition to t when you see the two symbols appear in the same equation. But for now, let's just say f of tau is equal to the mass times the velocity, which is just, the mass times the acceleration, I should say, which is just the first differential velocity with respect to time. Okay, let's rearrange that slightly, and we'll say that f of tau times d tau is equal to m times dv. Okay, now this thing here, well, remember, that's a force times a duration, or the time of which it was applied. We know that to be an impulse, right? So that's just an impulse. Remember the area underneath the force time history, and that's equal to m times dv. So what we're saying here is that, let me just highlight the fact that that's a velocity change. What we're saying is that an impulse induces an instantaneous change in velocity. Now we can interpret that, that's this guy here, we can interpret that instantaneous change in velocity as an initial velocity. So let's just put a note down here to say an impulse induces an instantaneous change in velocity dv. Now we can interpret that instantaneous change in velocity upon application of this impulse as an initial velocity. Now, and we're going to call that v0, an initial velocity. Right, so what does that mean? That means that we can say dv, which we're now choosing to interpret as an initial velocity, it's an instantaneous change in velocity, so initial velocity, is going to be equal to f of tau d tau over m. Okay, so now let's think where we are. We have a single degree of freedom system subject to some initial velocity, and we want the damped free vibration response. Well, we've almost certainly, if you're familiar with the sort of fundamentals of structural dynamics, you'll have come across that concept before, the concept of the free vibration or damped free vibration of a single degree of freedom system. It's one of the first things you learn when you start studying dynamics. And you can quite easily determine an equation for that free vibration response, and it's the following equation. If that equation is not familiar and you don't like equations just sort of dropping out of the air like this, I've derived this equation, and we go into great detail about the fundamentals of structural dynamics in my course, Fundamentals of Structural Dynamics. So if you want to get some of the background on this, go and take a look at that course. But for now, we'll assume that you're relatively happy with this equation. So what is it? It's just to summarize here, it is the u is going to be the response, right? The displacement, as opposed to v being our velocity. So we've got this term here, this exponential decay term is essentially modeling the decay due to damping. So xi here is the damping ratio. Omega n is the angular natural frequency of our system. T is just time. We've got V0, which is this same as this V0 here. We've got U0, which is the initial displacement of our system. We're typically going to let that equal to 0. You've got xi again, omega n again, and then you've got omega d here is the damped angular natural frequency. And then the rest of these terms, well, we've seen. So we've got a cosine term and a sine term. So all this is the equation for the free vibration, damped free vibration response of a single degree of freedom system, where we have left in our initial a term or a variable for our initial velocity and a variable for our initial displacement. So now we can start using this expression now, right? So what we're going to do is we're going to say let u0, the initial displacement of the system, is going to be 0. We're going to assume the impulse is applied at time tau, right? So this is where t and tau are sort of living in the same equation, you'll see now. So we'll say, assume impulse applied at time tau, okay, and then our initial velocity, we're going to let our initial velocity be the expression we've already got, which is, okay, so you plug all of these bits and pieces, plug those straight in there, and what are you going to get? You're going to get the incremental response, which we're going to call du rather than u, induced by the impulse f of tau d tau applied at time tau. All right, so that looks like the following, right? We've got du of t is equal to e to the minus xi omega n t minus tau, right? So t minus tau is now representing the time that has elapsed since the impulse was applied. Remember, impulse is applied at time tau, right? And then t minus tau is just the time that has elapsed since then. So we've got that damping term times all of this stuff in here, right? Right, so what is this? This is just the response t seconds after the impulse was applied. And anytime we see t minus tau, that's just the time since the impulse was applied. Okay, so we're nearly there. Remember, we said that the response, the overall response of our system, right, our single degree of freedom system, it's not the response due to one impulse, right? One impulse, which was this guy here, but it's the response due, the summation of responses due to every single impulse that got applied previous to the current time t, right? So we basically have to superimpose or sum up the influence of all of these responses. So that's our final step, and that's the step that results in the Duhamel integral. It results in the integral, essentially. So what we're going to say here is the final step is to sum up the influence of all impulses applied up to time t. Okay, and when we do that, we're going to get the actual overall response at time t, and that's equal to 1 over m times omega d times the integration between 0 and t of f of tau times e to the minus xi omega n t minus tau times the sine of omega d t minus tau d tau. Right, that is the Duhamel integral. Okay, so solving that integration is what's going to give us the response at time t. Alright, so we can make a couple of, just before we wrap up here, we can make a couple of key points here, right? So this is essentially an expression, this f of tau, this is an expression for the force, the loading that's going to get applied to our structure. Now, if f of tau is a simple function, well then we might be able to solve this integration analytically. Now that works for simple problems, but it's got pretty limited practical value in all honesty. Now, the other alternative is if this is a really complex function, right, a really awkward function, and you just look at it and you say to yourself, there's no way I know how to integrate that. It mightn't even be possible to integrate it analytically. Or if f of tau is not actually a function, if it's actually just a series of numbers, a series of values of force, so a force time history essentially, well then you can't do analytical integration on a force time history, it's just a sequence of numbers. So in both of those cases, a complex forcing function or a forcing function that's not a function but a sequence of numbers, well then we're going to rely on numerical integration. Now, numerical integration, although technically it's only going to be an approximation, it's going to be a much more versatile approach. So we're going to demonstrate both, obviously. We're going to look at an analytical integration in the next video, and then in the one after that we're going to look at a numerical integration, but it's going to be numerical integration that we carry forward because that is what is the most versatile method, if you like. Now, the last thing to say here before we wrap this up is that this relies on superposition. This whole Duhamel integral, we're relying on superimposing single degree of freedom, damped vibration responses. So, you'll have come across the concept of superposition many times in the past. And the caveat that always accompanies superposition is that you're relying on linear behavior, right? Your structural behavior has to be linear. Now, one particular, limitation that applies in the context of human-induced vibration is that we cannot model any kind of human structure interaction or feedback if we're relying on a Duhamel integral approach that relies itself on superposition, because that would be a non-linear behavior behavior due to coupling between the dynamic system, the bridge in this case, and the people that are generating the force on the bridge. And the most famous case of this is obviously your London Millennium Bridge, where you had a feedback between the crowd walking across the bridge and the oscillation of the bridge. The oscillation of the bridge altered the behavior of the crowd in such a way that led their ground reaction forces were increased or led to a larger force on the structure, exciting the structure more, and there was feedback thereby set up between the crowd and the bridge. Now, although the Millennium Bridge, and there's been many other cases of this human structure interaction and positive feedback, although it's quite a juicy problem from an engineering point of view, it's also quite rare, and in the vast majority of cases it's going to be absolutely fine to assume no interaction between your pedestrians and whatever structure, your people, and whatever structure they're walking on. Now, we'll talk a little bit more about that when we get on to talking about how to model the ground reaction force, the force due to walking on a structure. But just know for now, and in particular when we're dealing with vertical vibration, you're generally not going to have any real strong interaction between the vibration of the structure and the people walking on it. And so the Duhamel integral in this case is a suitable way to go. All right, so that's enough said about the sort of caveats and points relating to this Duhamel integral. In the next video, as I say, we're going to come in and demonstrate the analytical solution for a simple loading function. Right, so we'll leave that there for now.